42 billion cells are sealed inside your bones at this moment, not sitting on the surface. Sealed, each one walled into a chamber of mineral barely larger than the cell itself, connected to its neighbors by threads finer than a hair. The total length of those threads inside one adult skeleton comes to roughly 175,000 kilometers, long enough to circle the equator 4 times. Every one of those cells is doing the same job tonight, measuring how hard the bone around it is being squeezed, reporting that measurement to a demolition crew. 10 years from now, almost none of the mineral in your skeleton will be the mineral that is in it tonight. The shape will still be yours. The material will have been taken out and replaced, piece, by 2 cell populations that never stop working. What decides whether the replacement comes back as strong as what it replaced is a signal that takes about 1/10 of a second to produce, and most adults quietly stop producing it somewhere in their 50s. Start with what shows up on the outside. You are shorter than you were at 40. Not dramatically. A centimeter, maybe 2, maybe more. Shirts that used to sit right now sit a little long. The doorframe pencil mark from years ago is above the top of your head instead of level with it. Some of that is the discs between the vertebrae losing water, which is a separate story. Some of it is the vertebral bodies themselves, the blocks of bone, slowly compressing under the weight of a torso they have carried for 70 years. You have also noticed something about falls. A trip on a curb that would once have ended in a scraped palm and mild embarrassment now feels genuinely dangerous, and you have started walking differently because of it. Handrails have become something you use rather than something that is there. There is a particular kind of caution on wet tile that did not exist in your body 20 years ago, and your body installed it without asking you. And if you have had a scan, there was a number that was slightly lower than the last one. Nobody explained what the number was measuring. It was measuring mineral per square centimeter, and it had gone down, and the recommendation was calcium. That is where almost every explanation stops. Bones are made of calcium, bone is getting thinner, therefore the problem is calcium. It has the shape of an answer. It is close to being useless. Here is the arithmetic that breaks it. Your skeleton already holds about 1 kilogram of calcium. 99% of all the calcium in your entire body is locked in it. That kilogram is not just structure. It is the reserve tank that keeps the calcium concentration in your blood inside a very narrow band, because your heart and your nerves will not work outside that band. When blood calcium drops, the body does not politely wait for dinner. It sends a hormone that instructs bone to release calcium into circulation. So the skeleton is a bank, and the story you were told is that the bank is running low because you are not making enough deposits. In 2015, a research group at the University of Auckland, led by Vicky Tai, went through the accumulated trials on exactly this question and published the result in the BMJ. Increasing calcium intake, whether through food or through supplements, raised bone mineral density by roughly 1%, not 1% per year, compounding into something meaningful. 1% in the first year, and then the effect flattened and stayed flat. A 1% shift in density is not the difference between a bone that holds and a bone that does not, which means the supply line was never the constraint. There is a second piece of evidence that closes the door completely. Take a healthy 28-year-old, feed them perfectly, give them all the calcium they can absorb, and put them in bed for 17 weeks without letting them stand. Adrian LeBlanc and colleagues at NASA did this and published it in 1990. Bone mineral in the spine and the hip fell by close to 1% every month. Their diet did not change. Their age did not change. Their hormones were young. The only thing removed was load. Cosmonauts on the Mir station lost bone from the weight-bearing parts of the skeleton at a similar rate, and when Laurence Vico and her group in Saint Etienne measured them 6 months after landing, published in The Lancet in 2000, the bone had not fully come back. So, the problem is not the raw material, the problem is the instruction. And to find where the instruction is generated, you have to go upstream, one system at a time, starting from the bone you can see on a scan and ending at a cell you have probably never heard named. Layer 4 is the bone itself, and the first thing to correct is what you picture when you hear the word. A long bone is not a solid rod. It is a dense outer shell, called cortical bone, wrapped around an interior lattice of struts and plates called trabecular bone. In the head of the femur, in the vertebrae, in the wrist just above the joint, that lattice is the load-bearing structure. The struts are not randomly arranged. They run along the exact lines that the forces travel through that bone, so a vertical strut carries a vertical force and a diagonal brace catches a diagonal one. When bone is lost with age, the struts get thinner first. That is recoverable. Thinner struts can be thickened again. But past a certain point, a strut does not simply thin. It gets cut through. The demolition crew removes the last of it and the strut is gone, and the two ends it used to connect are now unbraced. This is the part that matters, and the part nobody mentions. Bone is only ever built on existing bone surface. There is no scaffolding, no formwork, no way to build a strut across an empty space. Once the connection is severed, the building crew has nothing to stand on. The lattice does not just get weaker. It loses members permanently, and the load those members were carrying is dumped onto the ones still standing, which are now carrying more than they were designed for. Which raises the obvious question: why is anything being demolished at all? Layer 3. The crew. Bone is rebuilt by a traveling team, not by one cell type, by two, working in a fixed sequence, in a unit that bone biologists call a basic multicellular unit. At any moment in an adult skeleton, somewhere between 1 and 2 million of these units are active. You are running a construction operation on that scale, silently, tonight. The unit leads with the demolition cell. An osteoclast is a giant, formed by several cells fusing together, carrying multiple nuclei, and it does something no other cell in your body does. It clamps onto the bone surface, seals the edges of itself down against the mineral to make a closed chamber, and then pumps hydrochloric acid into that sealed space until the pH inside drops to about 4.5. The acid dissolves the mineral. Underneath the mineral is collagen, and for the collagen the osteoclast secretes an enzyme called cathepsin K, which cuts the protein rope apart. In cortical bone, the osteoclasts advance as a group, tunneling forward through solid bone in a formation with the shape of a cone. Behind them come the builders. Osteoblasts arrive at the excavated surface and lay down new collagen, aligned, layer on layer, and then seed it with mineral crystals until the tunnel or the pit is refilled. Now the timing, because the timing is the whole problem. Demolition takes about 3 weeks. Reconstruction takes 3 to 4 months. The removal is fast, and the replacement is slow, so at any moment your skeleton contains a large number of open sites that have been emptied and not yet filled. That is normal. That is how it has always worked, including when you were 25. What changes is the completeness of the refill. In a young skeleton, the builders return the pit to almost exactly its previous volume. With age, and more sharply under low load, the refill runs slightly short. A fraction of a percent per cycle, nothing you could measure in one site. But trabecular bone turns over about 25% of itself every year, cortical bone around 3%, and the whole skeleton comes to roughly 10% annually, which is where the 10-year figure comes from. 10 years of small deficits, multiplied across 1 to 2 million sites, is not small. So the demolition crew keeps arriving and the building crew keeps under-delivering. Who is issuing the orders? Layer 2, the signal. For most of the 20th century, the assumption was that osteoclasts were recruited by hormones circulating in the blood. Hormones are part of it. They are not the local control. The order to summon a demolition crew is carried by a protein called rankle. A precursor cell circulating in the marrow becomes a mature osteoclast only when it encounters enough rankle. There is also a blocking molecule, osteoprotegerin, which binds rankel and takes it out of play. The ratio between those two is the throttle on demolition across your entire skeleton. There is a second signal working the opposite side. A protein called sclerostin, which does not summon demolition but suppresses construction. Where sclerostin is high, osteoblasts do less. Where it falls, they do more. 2 levers. One that calls in the crew that removes. One that holds back the crew that builds. For decades, nobody could say with confidence which cell was pulling them. In 2011, 2 independent groups, one led by Tomoki Nakashima in Tokyo, answered it. The main source of rankle in bone is not the surface cells and not the marrow. It is the cell sealed inside the mineral. And Alexander Robling's group at Indiana had already shown, in 2008, that sclerostin comes from that same buried cell, and that loading the bone makes it stop producing it. Which puts both levers in one hand. Layer 1. The osteocyte. When an osteoblast finishes building, most of them die or flatten out along the surface. But some get buried in the material they were laying down. Walled in, that buried cell becomes an osteocyte, and it does not die. It sits in its small cavity for decades, and it grows long, thin arms out through microscopic tunnels in the mineral, reaching for the arms of its neighbors, until every osteocyte in the bone is physically connected to the ones around it. Peter Buenzli and Natalie Sims put numbers on that network in 2015. 42 billion cells, roughly 3.7 trillion connections between them. 175,000 kilometers of cellular arm. It is, by connection count, one of the densest networks in your body, and it is entombed in rock. And it is not a filing system, it is the sensor. Here is what it senses, and this is the detail that turns the entire story. The osteocyte cannot feel the mineral squeezing it, because bone barely deforms. Under a hard step, bone strains by about 0.1%. That is far too small a shape change for a cell to detect directly. But those tunnels the arms run through are not empty. They are filled with fluid. When the bone deforms by that tiny amount, the fluid is forced to move through the tunnels, and it flows past the thin arms of the osteocyte and drags on them. That drag is the signal, not pressure, flow. Which has one consequence that explains almost everything that follows. Fluid only moves while the pressure is changing. Hold a bone under a steady load, and the fluid finds its new position, stops, and the signal disappears within seconds. Standing still is a load. It is not a signal. The person who first saw this was not a biologist and was not looking at cells. In 1867, in Zurich, an anatomist named Georg Hermann von Meyer was studying sawn sections of the upper end of the human femur. The femoral head sits on the shaft at an angle, so body weight does not press straight down through it. It presses off center, and the neck of the femur is loaded and bending. Meyer had drawn the interior lattice of that region, and the drawing showed curved arcs of bone crossing each other. According to the account that has been repeated ever since, Meyer showed the drawings to Carl Kuhlmann, a professor of engineering at the Polytechnic. Kuhlmann had spent his career calculating how forces travel through loaded structures, and he had recently worked out the stress lines in a curved crane. He looked at Meyer's cross-section of the human hip and recognized the diagram he had drawn himself for a piece of iron. The bone had solved the engineering problem, not approximately, in the same pattern. 25 years later, a surgeon named Julius Wolff took that observation and published it as a general principle in 1892. Bone, he argued, does not have a fixed architecture that it inherits and keeps. It has an architecture that is continuously reorganized by the forces passing through it. What Wolff could not know, and what the 20th century spent decades assembling, is that the reorganization is not the bone responding to force. It is 42 billion sealed cells reading a fluid current and voting. Now put the whole chain in one direction. A cell that is being loaded rapidly, repeatedly, gets fluid pulsing past its arms. It responds by dropping its sclerostin output, which releases the building crew, and by keeping its rankle output low, which limits the demolition crew. Local result. Refill completes, sometimes overshoots. The bone at that site holds or thickens. A cell that is not being loaded gets no fluid movement, nothing pulls on its arms. It has no way to know that the bone around it is worth keeping, because the only definition of worth keeping that bone has ever used is being used. Under sustained absence of that signal, some of those cells die. And here is the part that turns the loss from passive into active. A dying osteocyte does not fade out quietly. Its death and the disturbance around it triggers a local surge in rankle. Demolition crews are recruited directly to that spot. Disuse does not merely fail to build bone, it issues a removal order. That is why a young cosmonaut in orbit, eating well, and exercising the heart, loses skeletal mineral at a rate that would take a person on the ground years. It is why 17 weeks in a bed, does what it does. And it is why the bone that disappears first is always the bone that was carrying weight, the hip, the spine, the heel, while the skull, which carries nothing and never did, stays essentially unchanged in both cases. Your skeleton is not degrading, it is being decommissioned, section by section, according to a rule it has followed your entire life. Load it and it stays. Stop loading it and it gets recycled, because holding unused mineral is expensive and your body has never been sentimental. Now look at where the standard interventions sit on that chain. Calcium sits below layer 1 entirely. It is stock in the warehouse. Delivering more brick to a site where nobody has ordered a build changes nothing about whether the build happens, which is exactly what the Auckland analysis found. Vitamin D governs how much calcium crosses out of your gut, also supply. Necessary and genuinely worth knowing your level, and still not an instruction. The prescription medications used for thinning bone act at layer 2 and 3. Broadly, one family slows the demolition crew and another family stimulates the building crew. They work. Density numbers rise. Whether any of them is right for a specific person is entirely a conversation with a physician and not a subject for a video. But mechanically, notice what they are doing. They are adjusting the throttle. None of them restores the missing input at layer 1, which means that in a body that still never generates a loading signal, the underlying instruction has not changed. That is the reason downstream fixes plateau. You cannot supply your way out of a signaling problem. So what actually reaches layer 1? 4 properties, and they are unusual enough that almost nothing in ordinary modern daily life contains them. The load has to be dynamic, changing, not held. Fluid only moves while pressure is changing, so a static hold produces one brief pulse and then silence. The load has to be fast. The rate of change matters more than the size. A rapid moderate load moves more fluid than a slow heavy one, which is why a short drop onto the heels registers in the hip while standing under a heavy weight for a minute does not. The load has to be unfamiliar in its direction. A signal that repeats identically for hours becomes background, and the network stops responding to it, which is why walking on flat ground, for all its other benefits, is a weak osteogenic stimulus. Your hip has read that exact pattern several million times. And the load does not have to be long. This is the part that surprises people. In 1984, Clinton Rubin and Lance Lanyon showed that a small number of loading cycles per day produced essentially the same bone response as a very large number. The network saturates. It gets the message in a few dozen repetitions and then stops listening. Robling's group later showed something further, in 2002, that inserting rest between individual cycles rather than running them continuously increased the response substantially. The system needs the fluid to settle before it can register another wave. Short, fast, varied, with pauses. Now, honestly, what is established and what is not? The remodeling cycle, the two-cell crews, the timings, the Rankel and sclerostin pathways, and their origin in the osteocyte are established physiology, replicated across many laboratories and species, including humans. The loss of bone under unloading in bed rest and spaceflight is measured directly in people, repeatedly. The osteocyte counts are careful estimates built from measured densities extrapolated across the skeleton, not a head count. The fluid flow mechanism is strongly supported, but most of the direct measurement comes from animal models and isolated preparations because you cannot easily watch fluid move through a living human femur. The story about Cullman and the crane has been questioned by historians of medicine, who note that the anecdote grew in the retelling and that Meyer's original drawing was less exact than later versions suggested. The observation about trabecular alignment survives regardless. The anecdote may be tidier than the event. And the honest limit on the practical end, loading changes what happens at the sites that are loaded. It does not add struts that have already been cut through, because there is no surface left to build on, and it will not turn a skeleton at 75 into a skeleton at 35. What it changes is the instruction the network is sending during the next rebuilding cycle, and there is always a next one, which brings this to the only useful place it can go. The input the skeleton was built to receive is brief, rapid, repeated loading at the sites that carry weight. In practice, that means the feet, the hips, and the spine receiving a short jolt several times, with pauses between, most days. A rise onto the toes and a controlled drop back onto the heels does this. 10 to 20 of them, done deliberately with a moment between each rather than bounced continuously, delivers more signal than an hour of standing. Stairs do it, and stairs done at slightly different speeds do it better than stairs at one rhythm. Carrying something heavy on one side only, for a short distance, loads the spine and hip asymmetrically, which is a pattern the network has not already filed. Getting down to the floor and back up again loads the wrist and shoulder, which is otherwise almost never loaded at all in a modern day, and the wrist is one of the 3 sites where that lattice thins first. 2 things do not work: continuous unvaried repetition, because the network stops listening, and holding still under load, because there is no fluid movement without change. If you have had a fracture already, if you have been told your bone density is low, if you take medication for it, if you have had a hip or a knee replaced, or if you have a spinal condition of any kind, do not add impact to your day without your doctor mapping it for you first. Impact loading is an input, not a therapy, and which inputs your particular skeleton can take is a medical question with a medical answer. Everything in this video is mechanism, not medical advice. But understand what the mechanism means about time. Your skeleton is not a possession that wears out. It is a process, permanently underway, dismantling and reassembling itself around whatever forces you send through it. The femur you have at 80 is not the femur you were issued. It is the one your last decade of movement specified. In 1892, Julius Wolff wrote that the interior architecture of bone is not fixed, but is transformed by the demands placed on it. He had no cells, no imaging, no molecular biology. He had sawn sections and a drawing of a crane. He was right. He simply could not see who was doing the transforming. 42 billion of them, sealed in the dark, connected to each other, waiting to feel something move.